So let's take a look here at part C of example number 3. Suppose that Kyle has already waited 20 minutes for his bus, and he is still waiting. Have you ever had something like this happen, right? Like you're waiting for something to occur, and you're looking at your watch, you're checking your phone, you're like, gosh, I've been sitting here for so long, and maybe you start doing what I'm going to do here. You start considering maybe doing something else. In this case, I say, I'm going to consider getting a taxi or like an Uber or something like that to take him to the train maybe instead of waiting for a bus. Right? I mean, this is just getting annoying. I've already been here 20 minutes. I'm just wasting time. But I'm wondering if maybe I should just wait it out like another 10 minutes. Like, gosh, wouldn't it suck if you left and then like 2 minutes later the bus actually showed up? But maybe you've had scenarios that are kind of like this. So the question that we might ask is, what is the probability? What are the chances that I'm going to have to wait over another 10 minutes if I already know that I've waited 20 minutes? Well, what you kind of see in here is that there's actually a piece of information. There's some info about the scenario that we already know. And it's that I've already waited for 20 minutes. So really here I could say that what we want to find is what is the probability that I'm going to have to wait grand total, the 20 minutes I've already waited, but another 10 or more. So if you think about that, that'd be like waiting at the bus stop for like over 30 minutes. What are the chances that grand total I have to wait over 30 minutes, given that I've already had to wait over 20 minutes? Notice here x is being measured in minutes. So this might actually seem really difficult to compute. In fact, I'll even write that. This seems difficult to compute because it is a conditional distribution, or sorry, conditional probability. It is a conditional probability. But what we'll see is that actually if we take a look at what's on the next page, we can come up with a way to calculate this much more simply. Let's take a look. I'm going to kind of generalize the scenario that we have up above to try to see if there's some cool underlying property that's happening here. Suppose that I've had to wait t minutes, and I'm wondering if I will have to wait over s more minutes. So it's kind of like t right now is in the role of where my 20 used to be. Right? I've already had to wait this time. And the s minutes is kind of like playing the role of the extra 10 that I was going to wait up there. So what I'm really curious about is if I have to wait the 20 plus the 10, given that I've already waited over the 20. Okay, so I'm going to try to compute this kind of just in general. What's the probability that I have to wait over the sum, given that I've already had to wait over this value of t? And I'm just going to do this here in general so that way I can see this applying regardless of what numbers I have, like in the above scenario. Well, while this is a little bit tricky, we might remember back in chapter 3 we had a formula for computing conditional probabilities. The formula was that we dealt with the probability of both things happening at the same time. So we dealt with the probability of the first thing and the second thing, and then we divided by the probability of the thing that was given, which would look like this. Now, what's kind of interesting here is that we can simplify that numerator down a little bit more, because if I try to find the overlap between these two scenarios, I'll actually find that it's kind of rather simple. Let's go back up here to think about the two scenarios and how I can simplify this down. Because here I'm really asking something like, what's the probability that I have to wait over 30 minutes and I have to wait over 20 minutes? How can I possibly do both of those at the same time? What would be the only kinds of times that I can wait if I needed to be over 30 and over 20 at the same moment? Well, I couldn't wait like 25 minutes, right? Because while that's over 20, it's not also over 30. But I could wait 40 minutes, because that's over both. I could wait 100 minutes, because that's over both. So really, as long as I get past the 30 minutes, or the bigger one, everything's good. So really this numerator can simplify down to find any x that's bigger than this big value. Anything bigger than 30 is going to make both of these pieces work at the same time. Well, since I'm dealing with an exponential distribution then, I can actually fill this in. I know that I would just do e to the negative of this value times my value of lambda. And then I would divide by e to the negative of this value times lambda. Well, if I look at what I have in the numerator, I can kind of rewrite it a little bit. In the numerator, if I distribute in my lambda and my negative, I get negative t times lambda minus s times lambda. In the bottom, I have this. And if you really love exponents, which I'm sure you all do, you might be able to see that there's a different way I could actually re-express this numerator. It's negative t times lambda times e to the negative s times lambda. Now, the way that I can know that I can rewrite it that way is because you might recall that when I have something like two things with a common base, like in maybe something like this, if I multiply these together, you might recall that I add the powers. And if I added up these powers here, notice I'd be right back to where I started. But all of this can look really confusing and kind of seem really weird until you notice something awesome is going to happen here in this fraction. Don't we have something similar in the top and in the bottom of this fraction now? I mean, couldn't we almost imagine these pieces are the same? They can be canceled out. So all of this just turns into e to the negative s times lambda. But actually that's the same as just the probability that the variable x was greater than s. Okay, this is kind of weird. If you think about what we have here, this says, what is the probability? What's the probability of having to wait t plus s minutes if I've already waited t? That is, what are the chances of having to wait an extra, say, like 10 minutes, given that I've already waited 20? And notice that the answer is, well, however much more time you need to wait, it's the same as that probability. So if I want to say, should I wait another 10 minutes? Well, it's really just going to be asking the question, what's the probability that the bus comes in over 10 minutes? Essentially, this given information plays no role. It's what we refer to as a memoryless property. In an exponential distribution, the probability of having to wait a given period of time s, after already having to wait a time period of t, is really just the probability of having to wait s. That is, what's already happened makes no difference. So we can say that this probability here really just simplifies down to the probability of having to wait over s. Now, if this still seems a little bit confusing to you, don't worry. In the next video, we'll take a look at our last example for this section, example number 4, and we'll put exactly this property to use, grounded in a bit more of a context. So hopefully you can fully see the connection of this equality.